Okay, so now we're starting to get comfortable with the notion of a joint distribution being a surface or set of point masses over the xy plane that describe the probability with which a random vector takes on certain, or is in certain regions of the xy plane. And we've also seen examples of how to calculate probabilities by integrating the PDF over the relevant regions. Now we're going to see some other things that we can do with joint PDFs or joint distributions. And one of the things we can do is we can take the information that's embodied in a joint PDF or joint probability function, and we can extract the information that tells us about the individual distributions of those sort of constituent random variables. So let's suppose we've got a joint PDF of x and y, but we really only care about x for some reason. So how do we get the individual or the marginal distribution of x from that joint distribution? So let me first tell you how to do it, give you sort of the definition, and then we'll do some examples. Okay? Okay, so for discrete random variables, all we do is if we want the marginal distribution of x, and we have the joint distribution of x and y, we sum out over y. And I'll sort of give you the intuition for that in just a second. And for continuous random variables, we do, not surprisingly, the sort of continuous analog of that, which is that we integrate out over y. Okay? So what's the sort of intuition behind this? Well, for discrete random variables, you know, for a particular value of x, what we want to do is we just want to sum up the joint distribution over all the values of y to obtain the marginal distribution of x at that point. So if we want to know the probability that a random variable x is equal to little x, for instance, what we want to do is we want to sum up the probability that you know, from the joint distribution that the pair, well, for any possible value of y, all of the pairs for any possible value of y, we want to sum up those probabilities. And the sum of those probabilities gives us the marginal or individual distribution or probability for x. Okay? And then for continuous random variables, we just do the continuous analog of that. So this may seem a little kind of vague at this point, so now I think would be a good time to do an example or two. Okay, so let me turn to tennis. So Esther and I play tennis, and like a lot of sports, tennis players tend to rise or fall to the level of their opponent, and so it wouldn't be surprising to learn that we're more likely to both be playing well in a particular day or both be playing poorly, okay? Oh, by the way, that's the MIT tennis bubble. Have you guys played there? It's a very nice place to play tennis if you ever want to, you know, play tennis during the winter. Look into playing there. Okay, so let's see, where was I? So anyhow, it's not surprising that on any given day, Esther and I, if we're playing each other, we might both be playing well or both be playing poorly, okay? What would that observation about, you know, suggest about the shape of the joint probability function of our unforced errors by game? Okay, so for those of you who don't play tennis, just a tiny bit of background. A game is completed when a player wins 4 points by at least 2 points. And this scorekeeping has this sort of funny historical you know, character where we don't just count 0, 1, 2, 3. But an unforced error is basically when you know, Esther hits me the ball and it's a shot that I can get back, but I hit it into the net instead. Okay, so that's an unforced error. So obviously, if we're both playing well, we would have relatively few unforced errors. If we're both playing poorly, we'd have more unforced errors. Okay, so what does this observation that we're typically both going to be playing well or poorly suggest about the shape of this joint PDF or joint PF of our unforced errors by game? Any guesses? Well, if you think about it, the probability is going to be concentrated around values of x and y. So let's say x is the number of unforced errors that Esther hits, or that she's responsible for, and y is my unforced errors, the number of my unforced errors. So if we're both playing well or poorly, we would expect the probability to be concentrated around points in the joint PF where x and y have similar values. So we would expect there not to be a lot of probability for points where I have a lot of unforced errors and Esther has few, and vice versa. But we would expect a lot of probability to be concentrated around points where we have similar numbers, right? So exactly what might something like this look like? Well, here's one example. So I just made this up, obviously. This is not based on any long-term data that we've been collecting. Okay, so x, let's say x is my number of unforced errors and y is Esther's number of unforced errors. And what we see is there's a concentration of probability around this sort of axis where x and y have similar values. And very little probability here and very little probability up there. Actually 0, the way I've drawn it. Okay? Does that make sense? Okay, and apparently because we don't hit that many unforced errors, we're pretty good. Okay, so here's the graphical representation of exactly the joint PF I just showed you. So I just sort of drew what it would look like graphically. And now let's calculate the marginal distribution marginal distributions for both x and y. Okay? So remember what we said a couple of slides ago. All we want to do is add up over values of the other random variable to get the value of the marginal distribution for a particular x or particular y. So specifically, the probability that I make 2 unforced errors in a game is the probability that I make 2 unforced errors and Esther makes 0. Plus the probability that I make 2 and Esther makes 1, plus the probability that I make 2 and Esther makes 2, etc. Okay? So all I'm doing is just adding up along a particular value for x. Okay, so then we get, if I do that, and I do that for all the values of x, I get the following marginal distribution. So the probability that big X is equal to 3/8 is, the probability that big X is equal to 0 is equal to 3/8. The probability that's equal to 1 is equal to 5/16, and so forth. Okay? And it turns out that the marginal distributions of our errors are exactly the same. Okay? So I've just written this. Instead of writing both of the marginal distributions out, I just wrote it, that f sub x of little x is equal to f sub y of little y. Okay? And I want to also mention that I will never reveal the true distributions of our unforced errors. You can speculate if you want. Okay. Oh, and here it is graphically, okay? So both of the marginal distributions look the same, obviously.